Hey guys, and welcome back to another video. In this video, we'll be talking about linearization. Alright, so let's get right into it. Okay, so to begin with, consider you have the graph of some function that looks like this, right? And suppose you want to approximate the value of the function at some point x equals a. Alright. So how can you do it? Well, you can approximate it using a tangent line, right? That's reasonable enough. So if we draw the tangent line to this graph at this point, we get something like that, right? And so now we want to find the equation of this tangent line. Okay, so how do we do it? Well, we can consider point slope form. All right, so point slope form. And so point slope form basically is y minus y1 equals m times x minus x1. So where x1, y1 is like a coordinate point that you know is on the line, right? So some point on the line. And then m is just the slope of the line. Okay, m is equal to the slope of the line. So for our line right here, we do have a point that we know is on the line, right? We know that the point a, f of a, this point is on the line. So we have a point, that's good. So now we need to find the slope of the line. Well, in order to find slope, you need 2 points, right? But we only know 1 point on the line. So how would you find the slope? Well, it is a tangent line to the graph of f, so we could use the derivative. And so therefore, the slope of this line is simply just the first derivative of f evaluated at x equals a. So it's just f prime of a, okay? Because it's just, this is the tangent line to f at x equals a, and so by definition, that is equal to f prime of a. Okay, so that is the slope. All right, good. So now that we have a point and we know the slope, we can apply slope intercept, or apply point slope form. I'm sorry. So I'm going to call this line y equals L of x, some function L of x, right? So we have L minus y1, which is f of a, equals the slope, which is f prime of a times x minus a. All right. So this is the equation of this tangent line. All right. And so this is the linearization formula. So basically, what linearization is it allows you to approximate a function value at or near some point A. And so that's useful in many applications, right? So basically, this gives good estimates, gives good approximations near x equals A. All right. And then also it's useful, so it's most useful when, like, let's just say we don't know the exact equation of the function, but we know information about the function at some point x equals a, and you want to find estimates around a. So it's useful when, like, you don't, when the function is unknown. So when function is unknown, useful when the function is unknown, or when function value at a is hard to compute. So what do I mean by the second point? So when the function value at a is hard to compute. Well, suppose we have some, like, function f of x is equal to, like, the square root of x, right? And you want to evaluate, like, f of 11. Like, computing the square root of 11 is pretty hard, especially by hand, right? And this is, like, assuming we don't have any calculators or anything. So you can't really compute square root of 11. Or, like, another example is if, like, we had, like, g of x, let's say, is equal to, like, sine of x. And so then finding, like, g of, like, I don't know, like, let's say 0.75. Like, finding sine of 0.75 is also pretty difficult. Okay, so therefore, this is, like, cases when the function value at a is hard to compute. And so therefore we can apply linearization techniques to find the equation of the line at some x value close to this x value where we do know what sine of that is, or where we do know what square root of that value is, and then we can approximate it that way. And so this leads right into our next example, which is basically how do we approximate. So it's like how to approximate square root of 10, right? So assume like you want to approximate the value of square root of 10. You're not given any calculator, nothing. You just have to apply pure math, all right? So how would you do it? Well, so like the first step is I would just try to consider some function f of x equals the square root of x, right? And so then now I can rewrite this question in terms of f, right? So now the question becomes, what is the value of f of 10, right? So f of 10, like trying to find f of 10. Well, so we have square root of x, right? So is there any x value near 10 for which we do know what the square root is? Well, if we consider x equals 9, so f of 9 is just the square root of 9, which we know to be 3, right? F of 9 is 3. So maybe if we can find the linearization of f at x equals 9, and then you can use that linearization to approximate the f of 10. So that's what we're going to do. All right. So remember, for linearization, you need two things. You need the point that you know is going to be on the line. So in this case, we have 9 comma f of 9, which just simplifies to 9, 3, because f of 9 is just 3. And then we also need the slope. So the slope of the line at x equals 9, well, that's just simply f prime of 9, right? Because it's the tangent line at x equals 9. So let's evaluate f prime of 9. So f prime of x, so this is just square root of x, right? So we can rewrite this as x to the 1/2 power. And so then we can use power rule to get f prime of x is 1/2 x to the negative 1/2, which is just 1 over 2 root x, right? And so f prime of 9 is 1 over 2 root 9, which is just 1 over 6. So m is just equal to 1/6. All right, and so now we can use our linearization. So we get that L minus f of 9, which is just 3, is equal to the slope, which is f prime of 9, which is just 1/6 times x minus 9. All right, and so now if we're trying to solve for L of x, we get L of x is equal to 1/6 x plus 3 over 2. All right. So now this is the equation of the tangent line of f at x equals 9, right? So if we like try to draw a graph of this, square root of x looks something like that, right? And so let's just say x equals 9 is right here, and this is 10. So right here, if you draw the tangent line, ooh, it would be something like, I'm gonna draw this again. Right, more or less something like that. So this is L of x, and then obviously this is f of x. So note how at x equals 9, L of x is equal to L of x, f of x, sorry. So L of 9 is equal to f of 9. But at x equals 10, there's like a small gap, right? But the gap is relatively small still. So we can approximate L of 10. So we know that L of 9 is equal to f of 9, right? We've already established that. But then we can also approximate L of 10 is approximately f of 10. So that's what we're going to do. Basically, we're going to find L of 10, which is, let's see, 1/6 times 10 plus 3 over 2. So that gives us 19 over 6. And so therefore we can say that f of 10, which is just the square root of 10, is approximately 19 over 6, right? So this is a good approximation for square root of 10, right? Using this linearization method. Another thing I want to point out is that this linearization method like only gives good estimations if you're close to the original x value. So for example, we took the linearization at x equals 9, right? So this only gives good approximations close to 9. So the closer you are to 9, the better approximations it gives, and the farther away you are, the less good approximation it gives, right? All right. So that being said, let's move on to our next example. All right. So this is our next example. So we have a car is accelerating down a track, and it has traveled a distance of 180 feet at time equals 4 seconds. Okay, and at time equals 4 seconds, it has an instantaneous velocity of 110 feet per second. And our goal is to predict the car's position at t equals 5 seconds. All right. So again, first let's just see what the problem is asking us. Well, at t equals 4 seconds, we know a lot of information about this function, right? So we know that the distance that is traveled is 180 feet, instantaneous velocity 110 feet per second, etc. And now we want to predict the car's position at 5 seconds. Well, let's note that we aren't given the position function, right? We don't know what the position function is for this case. And we can't even find the position function because we're not given the acceleration function or anything. So therefore, we must rely solely on approximations. Okay, so now that we know that we need approximations, which approximation technique should we use? Well, we can use linearization, right? Because note that t equals 5 seconds is pretty close to t equals 4 seconds. So that's why if we use linearization, the approximation at t equals 5 seconds will be pretty good, given the information we know about t equals 4 seconds. But like, let's just say this was at t equals 10 or t equals 20 seconds, then linearization might not be as good of a technique, and we might have to resort to other approximation techniques, right, that we haven't obviously learned yet. But for this scenario, we can use linearization because the two t values are pretty close to each other. So that being said, let's identify the point that we do know. So again, just to point out, we're finding the linearization at t equals 4 seconds, and then using that to approximate the value at t equals 5 seconds. All right, so at t equals 4 seconds, we know that at t equals 4, our position is 180 feet. Okay, so, and just like some common like notation, I guess you could say, is that in like these types of like physics, PVA, position velocity acceleration problems, S of t usually denotes the position function. So this is like the position function. And then V of t is the velocity function. And then A of t, which we don't need to use in this case, but that's the acceleration function. All right, so that's just like for reference. If I ever write that down, just know this is what it means. All right. So basically what I'm trying to say is that this is equal to 4 S of 4, right? So the position at S at 4, S of 4 is equal to 180 feet. That's what this is saying. And so then also I will mention one more important thing is that the velocity function, so v of t, is the first derivative of the position function. So v of t is equal to s prime of t. All right. And then similarly, the acceleration function is the first derivative of the velocity function. So a of t is equal to v prime of t. And so this means that if we differentiate v prime of t, if we need to write if with like any case we need to write a of t in terms of the position function, it's just equal to the second derivative of position. So s double prime of t. All right. So these are some relationships you should keep in mind. All right, good. So therefore, we have the point 4, s of 4, which we know is 4,180. And so then now we need to find the slope at t equals 4 seconds. Well, the slope is just equal to s prime of 4, right? But they don't mention any derivative of position function in this problem. So what is s prime of 4? Well, if you come down here, we note that s prime of t is equal to v of t. So s prime of 4 is actually just equal to v of 4. So just the velocity, the instantaneous velocity, that is to say, at t equals 4 seconds. And that they do get, right? They tell us that the instantaneous velocity is 110 feet per second. So this is equal to 110 feet per second. All right, good. So now we have the slope at t equals 4 seconds, and we have a point. So now we can use linearization to find the equation of the line. All right, so we have L minus 180 equals the slope, which is 110, times t minus 4. And note that this time I'm using t as the independent variable because we are dealing with time, right? So we get that L of t is equal to 110t. Let's see, this is minus 260. All right, so this is our linearization function. Well, no, we're not done yet because we want to predict the position of the car at time equals 5 seconds. So what does that mean? Well, simply that all that means is that we have to find L of 5, all right? So let's go ahead and do that now. So L of 5 equals, so we have 110 times 5 minus 260, and so this gives us 290. And so our units in this case are just feet, right? Because we're trying to find the position. So therefore, we can predict that the car's position at time equals 5 seconds will be 290 feet, right? So this is the answer, and we're done. Okay, good. So yeah, hopefully this video was helpful to you, and I understand like the implications behind linearization and how we can use it. And if you did, please make sure to leave a like and don't forget to subscribe. I'll see you guys in the next video.